Today's my pleasure to introduce tonight's speaker, Thomas Evangelist. He's a member of the MHAA. His topic tonight is titled Chemical Analysis on the Europa Clipper, and I'll let him tell you more about that. Mr. Evangelist is currently the assistant principal of the physical sciences at Brooklyn Technical High School. He's been an educator for 29 years, also an author for McGraw-Hill, and he's also an adjunct lecturer for CUNY Brooklyn College. He has a BA and MA in chemical education and certification supervision in science education from Brooklyn College. And he has a C Star. So with that, let's give a warm welcome to tonight's speaker.
Thank you. All right, very good. And actually, I don't know how it's possible. I got that C Star at $3.99. So I don't know if I got the introductory price. I had to wait 18 weeks or 14 weeks for it, but I definitely got. Okay, here we go. All right, so just something that came up at Astronomy Club early this year was the Europa Clipper, scheduled to launch, I believe, in October of this year, and return data, I think, in 2030. Okay, good. All right. Thank you again for the introduction. See here, yes, I'm a Brooklyn boy. Just came up here about 6 years ago, just paid off my mortgage. So I own the house now, just finished that out. But 3 degrees from Brooklyn College, spent all my college years there, 196.5 total credits in one school. After 12 years, student, adjunct, it was time to go. And well, part of my master's I did at night, but I did 1 semester full time. And over a number of years as a teacher, I finished that master's degree. And over 12 years at Brooklyn College, and then all of a sudden they saw me come in as they see you come in as a new freshman in college. They see me leave as an assistant principal. So it was pretty good. Almost there. 3 more years, August 1st, 2027. Last time I was here, I was saying, oh my God, I got 4 years left. Now it's real. 3 years, the landing gear is down. 3 green lights on the pilot's on the dashboard. Now it's real. And to give you an idea, like Bart had just said, an author from the McGraw-Hill Companies. Actually, I just retired, quotes from McGraw-Hill. So close to retirement, it actually pays better for me to do work for the school that's pensionable. So I just parted ways. I finished the mortgage. I just parted ways with McGraw-Hill, and we'll just I'll stick with the school for now until I'm done. So, all right. I don't know if you ever get a chance, visit NASA's website. Okay, the kids go through it routinely. They show me things, and this one Europa Clipper came up in discussion at Astronomy Club, and as NASA says there on their website. Am I moving around too much? Okay, that's me. Okay, so it says Moon of Jupiter potential for life, and then whenever they say potential for life, we're always talking finding water. Okay, that's really the underlying thing. Not to sound like a used car salesman, but it is. If you're going to spend $5 billion on a mission, it had better be nicely equipped. Actually, you better justify that price tag. But some things that it has: stereoscopic imaging, infrared light to detect warmer regions. Kind of like at the hospital, you go in and they use the beam on your forehead and they take your temperature, kind of thing. Okay, oh, good. All right, go ahead, admit. Yeah, do what you gotta do. I work in a public school. You can't scam me with disruptions. Okay, so just don't throw a chair at me. And then a magnetometer. Depth, salinity, and ice shelf thickness, of course, depth and salinity of water. Okay, again, just magnetic field measurements, gravitational measurements, and ice penetrating sonar to look at ice thickness. Again, so it's all about finding the water. But all these here, there were 4 instruments that caught my eye as a chemist, or a chemistry background. One of them was this mass spectrometer that's going to be used to identify gases around Europa. This thing is pretty nice looking. Nothing like mass spectrometer I've ever seen. This thing is pretty nice looking here. and it tells you why the damn thing is $5 billion. But just a quick overview of what mass spec does. Okay, so gas molecules are going to be racing into the instrument. Okay, and what it's going to immediately do is you want to knock an electron off those gases to make them positively charged. And then from there, they're going to be accelerated through a drift tube. Okay, and the lighter the ion, the faster it moves through, and the sooner it'll be analyzed when it reaches the detector. Okay, there's a common theme here because there's actually two mass spectrometers on this, which caught my eye. So here's the first one, mass spec. The other one is SUDA, okay, the surface dust analyzer. And this is more my area, organic spectrometric identification of organic compounds. This is what really caught my eye, how this is going to work to sort compounds out and help identify them using mass spectroscopy. So I just wanted to give you a quick overview of how this works. And we're just going to keep it very, very light. Once I get past this here, again, it's the same stuff. This, what we want to do to analyze molecules. If we look at the second paragraph, the first quotation, it says we're going to, the individual molecules are going to be ionized. Okay, that's the first thing. You hit them with a beam of electrons, get them positively charged. They go through an electric field, and then they funnel down through a detector. And from there, this is what really caught my eye, is the third line from the end. Okay, look to resolve amino acids. Okay, that's one thing, but biomolecule is the last word there. Okay, so let's see. I'm going to show you what would be a good result from all this. The results will be back in 2030. In fact, I was joking with Steve, mark me down for November of 2030 as your guest speaker. Okay, I'll have plenty of free time on my hand, but I'm curious to see what happens when this data comes back. Okay, I have to wait 6-ish years, but hey, when you're retired, hey, whatever. So, okay, but this is just an overview of what's going to happen to these molecules. They're going to enter the mass spectrometer, and they're going to be hit with a beam of electrons, and they're going to be accelerated with, and then deflected by a magnetic field. The lighter ones get deflected more, the heavier ones get deflected less. Okay, I can't say exactly that this is, you know, exactly. NASA did not give me a user manual. Okay, and I'm not breaking into the Jet Propulsion Lab in Southern California with a screwdriver and a wrench to open the equipment up, but I'm just going to give you an overview of how this stuff works. It's quite interesting, and we'll talk about, you know, what would optimal results be. But in the beginning, there were isotopes. Okay, did I sound like a chemistry teacher? Okay, anytime you see the word iso, something is going to be the same and something is going to be different. Okay, like an isosceles triangle. Okay, two sides are the same, one side is different. So anytime you see iso, isomers, isotopes, okay, and the other mistake people make is when they analyze an isotope, they look at the electron numbers. Okay, always focus on the protons and neutrons and the nucleus of the atom when you talk about isotopes. But what makes these three atoms isotopes of carbon? They have the same number of protons, it's all carbon, but they have a different number of neutrons. Okay, and that's what makes the mass number 12, 13, and 14. That's what makes the mass numbers differ. Okay, how are we doing till now? Is that okay, isotopes? Okay, because it's going to get a little messy. Okay, now, so we're going to be on a mission tonight. Okay, we're starting our own mission to Planet X, and we're going to be looking for bromine and chlorine. And I'm going to show you exactly how to do it using these instruments. Okay, bromine has two isotopes, 79 and 81. Okay, they both have 35 protons. The number of neutrons will differ, 44, 46. But what really catches my eye here is that if you run into a bromine atom, you have a 50-50 chance of running into the 79 isotope and about a 50-50 chance of hitting the 81 isotope. Okay, so there you go. It's about an equal mixture of them in nature. Okay, with chlorine, a little bit different. Isotope number 35, 75% naturally occurring says chlorine 35, and 25% is chlorine 37. That's numbers, okay, that's Mother Nature has provided. Okay, we can't change that. You'll notice that the 35 isotope is exactly 3 times more abundant than the chlorine 37. Okay, 75 is exactly 3 times greater than 25. Okay, hope I'm not going too fast, but when you do mass spectroscopy and it involves these elements, if you look at the bromine's mass spec pattern, you'll see how the 2 peaks come out to be 50-50. Okay, which is exactly the numbers in the abundance percentage is about 50-50. So sure enough, the peaks are about 50-50 in height. The chlorine we said was 75-25. So one of those peaks should be 3 times greater than the other. And sure enough, it is. Okay, these are the 2 most stark ones you'll find in mass spec. That's why I picked these. After this, isotopic abundance can get really, really messy. But if you just keep these 2 in the back of your mind in our mission to go find bromine and chlorine on planet X, okay, because here's your first quiz. Do I have bromine in here? Do I have chlorine in here? Do I have neither? I wouldn't do both. That would be cruel. Okay, that would be mean for sure. Oh, don't be shy. Ah, okay. I hear some answers here. All right. Is there bromine in here? Is there chlorine here? Let's go back. Okay, I'm a visual learner. Okay, I remember what I see, that's for sure. Okay, it saved me on my physics 2 exam in college. It's just remembering one picture from the textbook. It saved me on like a 4-part problem. Okay, so if it's bromine, we should have equal heights approximately. And if there's chlorine, there should be a 3-to-1 ratio. Okay, let's do it again. Do we have peaks of equal heights? Yes, okay, there they are. Okay, it's 79 and 80. Okay, so this goes back to those masses of bromine. It has a mass of 79 and a mass of 80. Okay, so okay, when you see here, you see there are peaks at 79 and 81. I'm sorry, I said 80, I'm sorry, 81, I apologize. You have those 2 peaks of equal height at 79 and 81. Okay, this is the data. These are things that, these patterns that NASA is going to be looking for when identifying the elements or the compounds that are hitting their mass spectrometer or entering their mass spectrometer. Okay. The other thing that I see here is that there's also peaks at 94 and 96 of the same height. Okay, but just when you see those 2 peaks of almost equal height and they're 2 apart, that's indicative of bromine. Okay, so this here is actually a bromine compound. It's bromomethane. Okay, very, very simple compound here, but this is how NASA is going to be able to do it when they get these results back. Okay, it's all by studying these patterns that are generated within the mass spectrometer. Okay, whew, tough, huh? Okay, welcome to my graduate years. Professor hands me 7 compounds in test tubes and says, you got 15 weeks, tell me what they are. Okay, that's why the lab meets 10 hours a week. Okay, how about this one? What do you think? Does it have bromine, chlorine, neither? What do you think? It has chlorine in it, yes. Okay, one of the peaks is 3 times as high as the other. Okay, so the percentages of the peaks give it away, or at least for me, I'm obviously more experienced, but I look at this and I see, okay, one of them is 3 times higher, but I don't see any 35 and I don't see any 37. You're saying, how could that be? The other one had the 79 and 81. How do you see chlorine in this one? There's a little trick. Anybody see the little trick? Do 2 subtractions. What do the numbers come out to be? 50 minus 15? 35. 52 minus 15, 37. There you go. So there's your 2 chlorine isotopes. Okay, this is how it's done in finding the elements that are present, okay, in the molecules and in the and the gases, and even if you're using the plasma mass, it's a pure element. So this is what the kind of thing that NASA is going to be getting back and interpreting. So I actually have a good one here. If you have a periodic table, okay. Other things that can be done, minus the way I just did the bromine and chlorine. But if you have a periodic table, okay, on your cell phone in front, if you want to pull one up, okay, I'll give you a second there to do that. Okay, Dad, give him his phone. You have one? There you go. Good. We have one here, but it's a little. It doesn't even have element 118. Oh God. All right. Anyway. Okay. By the way, if you can tell me why bromine and mercury are in blue on the periodic table, you get bonus points. Okay. So here's an element. It's mostly an isotope, mass of 90, but there are just a few isotopes out there that are 91, 92, there's a little bit of 94, there's a little bit of 96. So if we start to average them out, it's mostly 90, but it'll be above 90, it'll be close to 90. Maybe it's a mass of 91, maybe it's a mass of 92. Is there an element out there with a mass of 91-ish, 92-ish? Not atomic number, by the way, atomic mass, okay? See, I told you, Steve, if you sit there, you're gonna have to, I'm making Steve do work in the dark here. So, no, element with approximately a mass of 91, 92. What do you got, Luke? Close. Zirconium, attaboy. There you go. That's why I was a guest speaker at his school. What a great experience. So it is zirconium. By the way, the one time I go visit your school, it's yearbook picture day. And I just happened to be presenting. I ended up in his high school yearbook photo for astronomy club. Go figure. But this is how mass spectrometry works. You get back, if it's a single element, you get back this data table. And then from the relative abundance, you can figure out and take an average, and you can actually figure out using a little bit of math, nothing hard, some algebra, and you can actually figure out which element has just hit the detector. Okay, it's that good. Okay, now to think that there'll be two of these working at the same time up there, collecting all these samples and analyzing them. Wow, smoking hot, $5 billion worth right there. Forget the other instruments, okay? So, but no spectroscopy, at least it should be done on its own. Okay, chemists, we always use a range or a number of spectrometric methods to figure out what it is, because it's almost like I said, the professor gives us 7 different compounds and says you have 15 weeks, go figure it out. You almost have to be a lawyer or a forensic scientist. You almost have to prove beyond reasonable doubt, any doubt, that this is the chemical that was handed to you. So you have to use multiple mass spec, methods. So, but or spectroscopy methods. But what would we be looking for? If you're looking for life, I would say go for the amino acids. Okay, wouldn't it be great if data came back saying, hey, we've detected amino acids. If you have amino acids, you have the building blocks to proteins. Okay, and this here is the most simplest amino acid, glycine. I just, if something like this were to come back and this were detected, that would be monumental. Okay, $5 billion monumental right there. But you could see this is a far cry from that bromine and chlorine I showed you with just, 3 peaks here and 5 peaks there and equal heights. This gets quite messy. The more complex the molecules get, you really need a pro to analyze these. But looking at this, the base ion is 30. This here looks like to lose some sort of carboxylic acid and the other part of the molecules left over. But anyway, a lot of analysis can be done just from these few numbers here. So glycine would be NH2, CH2, COOH. You're welcome. Okay. And that COOH will probably rearrange when it gets cut off into carbon dioxide. So, all right. Yeah, it can get quite messy, this stuff. We're not going to do McLafferty rearrangements tonight, that's for sure. Okay, all right, so like I said, no spectroscopy goes on it. You just don't use one, you use a number of them. The other technique that to determine structure is infrared light. Okay, and the infrared spectrometer, actually, I have one sitting on my desk at work. Crazy enough, I'll show you. I got a great story for you how this works. But it's unbelievable. If you just shine light through a compound, you'll know how much went in, and you could detect how much came out and what the difference is. And from there, you can actually start to do a chemical analysis. But right from NASA's website, when they use IR on the Clipper, what's going to happen is different atoms and molecules will emit, absorb, and reflect various wavelengths of light in telltale ways. I'm going to show you how that works in a second, but I love this second statement though here. Light carries information about materials it has interacted with. That is so true. And okay, so they're going to shine infrared, and there'll be some ultraviolet. I'll go to that later, but the infrared light is going to be bounced off the surface. And from there, you'll see how much comes back. It's unbelievable how this stuff works. So literally every molecule has its rotations. It has the way of moving. The bonds could be moving. They could be scissoring. They could be wagging. Okay. And each frequency of light can modify those movements that a molecule makes. And we could see how much light is absorbed and then detected. So here's the key point. This is exactly what I put on the board in class. Okay, the key point for the kids. Actually, we do offer organic chemistry in our high school. It's 3 45-minute periods a day. So this is okay for one semester. So we teach the kids this here, and this different types of bonds between different types of atoms absorb a different amount of lights at different wave numbers. Okay, wave number is the chemist frequency, if you will. It's cycles per centimeter. But the thing is, each arrangement of atoms absorbs its own frequency of light, and we can learn so much about compound just from this. Okay, don't get too hung up on the numbers here, but I'm just going to go through some simple ones. I'll tell you a good story here. But if you have a carbon to hydrogen single bond, okay, for example, you get these big peaks at 2,900 reciprocal centimeters. Okay, this you'll see all the time for organic molecules because they have so much carbon and hydrogen in them. Okay, if you switch out the carbon and now put in a hydrogen, you could see how the peak grows in width. Okay, much bigger. This one, okay, between carbon and hydrogen, a long, narrow, sharp. Okay, whereas the oxygen to hydrogen, it broadens. Okay, and then if you have carbon to oxygen, you get these strong, sharp peaks at about a wave number of about 1050-ish. Okay, so what can you do with something like this? Well, put the pieces together and you can actually start to put molecules together. So once upon a time, I get a phone call from my calm, rational principal back in the day, and he's screaming his head off to get down to the dean's office. Okay, and a student brought, instead of a bottled water, the bottled water was filled with gin. So they were actually drinking in school, and the student had passed out. Now it spills into the dean's office, and my radio, the principal screaming over the radio, get down there, get into the dean's office, take samples and analyze it in that machine you have on your desk. So, all right, so this is exactly what pops up. Now, how do I know it's in alcohol for sure? Okay, there's the OH, there's that broad OH peak. Okay, that's telltale of oxygen to hydrogen. Well, that tells me I have an alcohol. Now, how do I know the student was drinking alcohol, ethanol? Well, if they drank any other alcohol, they either be dead or blind. So the mere fact that the kid was still alive is that they were drinking alcohol. But again, there's that peak at 2,900-ish, 2,980, and there's the peak at 1050 or 1055 in this case. So look at the molecule though, in the bottom middle, it's in green. It has oxygen to hydrogen. And sure enough, a peak comes up at 3391, that oxygen and hydrogen are present. Okay, you can't fool this. When you use light, it's going to be detected it analyzes the whole thing clean for you. I have carbon to hydrogen. Sure enough, ethanol has carbon to hydrogen, and there's an oxygen bonded to a carbon. And sure enough, it comes up. So you can't hide anything in a chemical analysis from IR. So you should have seen the parents though at the principal suspension hearing when they saw my printout attached to the report. Good God, I did not make friends that day. That's for sure. But it was worth the $22,000 from our alumni foundation to give us one of those. Actually, we have two of them now. So, all right, the one on my desk, nobody touches that one. That's mine. But anyway, there are other things that you could use. And again, I'm building towards finding this amino acid business. So C double bonded O. Okay, my last one was C single bonded O. It gave you a peak at 1050. But if you have a C double bonded O, now you get a strong sharp peak at 1710-ish. Okay, so now you'll know if your molecule has C single bonded O or C double bonded O. Now your analysis can get deeper and deeper. Okay, and I mean, you can have C double bonded O to an OH. Okay, you can get some different peaks here, much like OH and C double bonded O. So you can get all this analysis done. And then even with nitrogen, here, nitrogen is unmistakable. Nothing else gives you those two peaks at 3,400. Now, if you see that, it's definitely nitrogen with two hydrogen. There's no mistaking it. Okay, if you see something like this at 1,600, that peak all the way on the right, there's no mistaking it. Okay, this is why it's well worth having IR on board. Now, what would be ideal, okay, is because amino acids, once again, these are the building blocks of proteins. This is what we're looking for. It has the NH, it has the CH, it has the C double bonded O, C single bonded O, O to H, all these things. What would be ideal, once again, I'm just taking glycine as an amino acid. Man, if we could see something like this come back, okay, if something from the IR analysis comes back like this, this is what your typical analysis of an amino acid looks like. Okay, and if data like this comes back, that would be, again, once monumental. Okay, if you could find one of these in there. So well worth the wait. Well, 6 years, we'll find out. Okay, I'm going to actually appeal to my friends here today. For those of you who have a light pollution filter for your telescope. Okay, this is our last type of spectroscopy. This is UV spectroscopy. Here, the light is going to be passed through a slit, and then it'll go through an optical grating and all that, and it'll be analyzed. A little bit different, but still the same principles. We're not using IR, we're using UV vis, but there's this whole setup inside to get the light exactly the way you want it. It goes through two slits to make sure it's monochromatic and all that stuff. But the thing here is now we're working. Okay, if you know, we have visible light, okay, past red, you have infrared, and then on the other end, past violet, you have ultraviolet. So different energies are involved. So because UV light has a much higher energy, you can actually get different information out of a molecule than you can with infrared. Infrared, how do you know it's low energy? Look, if you use your garage door opener, no one ducks from the radiation. Okay, if you use your remote control, no one's going to duck from infrared radiation. Okay, that's a much weaker light, and it impacts the molecules in a different manner. This is high energy. Okay, this is UV. This is why everyone should be covering up at the beach and protecting yourself from sun's rays. Okay, in fact, Richard Simmons died at 76. What was it? What was the cause? Skin cancer. Okay, I thought he was going to live past Jack LaLanne. I was sweating to the oldies there, but so before we could do any analysis using UV vis, I just want to talk to you quickly about conjugated systems. Okay, and in class we sing the conjugated system song, and the kids just look at me funny when we do so. All it is double single, double single, double single, double single, double single. And they look at you, like, what do you mean? Something about having a double bond followed with a single bond, then another double bond in a row in a molecule is absolutely positively excellent at absorbing UV light and visible light as well. So let's just look at some examples. You see here on the left, you see how the left column has a double bond and then a single bond in purple and then another double bond. Okay, that's a conjugated system. It's going to absorb UV light and visible light better. Okay, whereas on the left, I'm sorry, on the right, pardon me, you have a double bond, two singles, and then another double. That's not a conjugated system. Okay, it's not going to absorb UV light as well. Okay, so PABA. Okay, products are now PABA free. Anybody know what PABA was used for? No, no. Para-amino benzoic acid is actually what they put in sunscreens. Okay, and it makes sense. You're looking to absorb UV light. So look at the molecule. It has a double bond to the oxygen, then a single bond to the ring. Then inside the ring, benzene, you have a double, single, double, single, double, single. So actually, this is vitamin B10. What was happening though is I probably used way back in the 40s, but people using para-amino benzoic acid, you could have a skin reaction to it, an allergic reaction to it if you're sensitive to it. But this stuff does a great job at absorbing UV light, and no wonder it was used in sunscreens. So if you look at the big curve, and you see here on the bottom, on the x-axis, the 240 nanometers is where it starts to absorb. And it's good to absorb through 310 nanometers. Look at the top middle, that's exactly where UVB radiation is. So no wonder they put it in sunscreens. Okay, it was absorbing all your UVB radiation. However, can your sunscreen just use para-amino benzoic acid? Look at the graph. What else is missing? Yeah, UVA. Okay, so para-amino benzoic acid on its own is okay to absorb UVB, but you'll need a second compound in your sunscreen to absorb the UVA. Okay, so para-amino benzoic acid on its own is not good enough. So your sunglasses. Okay, this is polycarbonate. Okay, this is the, oh my God, the name of this structure, bisphenol A, I believe it is, and the polycarbonate's the longer chain. How I know that off the top of my head, don't ask. Okay, but you see how much double, single, you see look at the two rings. You've got a double and a single, a double and a single, double, single, all the way around and around. Well, no wonder UVA and UVB can't get through your sunglasses. Okay, it's this molecule that's protecting your eyesight. Okay, so this is what we're looking for as chemists. If these wavelengths don't come back or absorbed, we'll know we have these larger conjugated systems that absorb light. And the more complex molecules we find with the Europa Clipper, the more we can start to say, yes, there's a higher probability of life. Okay, now I promised I would appeal to the astronomers in the room, and I did. Okay, so promises, promises. All right, here we go. Look at the bottom. Okay, common light pollution emissions. I'm from Brooklyn. You don't have to give me a lecture about light pollution. Okay, it's amazing. I took a picture of anything. Okay, but by the way, the C Star, get it because it takes care of all the light pollution stuff for you. So more reason to spend $600 on it. But anyway, you see the two light pollutants right below 400 and 440. Okay, when you make a light pollution filter for your telescope, chemists purposely design it so that there's the conjugated system and the right compounds to absorb UV light in that area. So those common light pollutants don't reach your eye. Okay, and then from about 540 all the way up to 650-ish or 625-ish, you see how it's designed to have other compounds in it to absorb those wavelengths. But what did they not put in your filter? Okay, in your light pollution filter, they did not put compounds in to absorb where hydrogen beta and oxygen 3 can be absorbed, so that you can look at the heavens and see these lights coming in from the gas clouds. Okay, have you seen these before in your light pollution? Okay, they give you these pamphlets. Okay, and they're outstanding. I sit there, I read them all the way through how they design it. Okay, absolutely positively amazing how these things are designed. You have to have the right compounds, the right mixture of compounds, and it'll absorb the light. So, okay, let's go back to 4th grade, or even sooner than that, 2nd grade. Okay, the science teacher in public schools in New York, the science teacher used to come in once a week. Okay, she used to travel to every grade and every class. Okay, and one of the first thing your science teacher talks about is, oh, plants absorb blue light and they absorb red light best. And then all the kids do the experiment for the science fair. They wrap the plant in red cellophane, blue cellophane, green cellophane. Okay, and the plants wrapped in green cellophane die. Well, now we know why. Okay, if you take a look at the chlorophyll A and chlorophyll B, if you look at the bottom, they don't absorb green at all. That's because their conjugated systems, or the bonds, are just not aligned properly, or just don't have the right structure to absorb there. But plants, the chlorophyll A and B, but look at the absorbance at blue and look at the absorbance in red. Okay, so if you're going to have that, you're going to grow those plants, a mixture of blue and red light is the way to go, of course. So when you look here, okay, the molecule on top, that's carotenoid, that's your carrot. Okay, sure enough, carotenoids, yeah, it's in the blue, almost to the green area. But look at the complexity of what makes your carrot orange. Okay, it's that compound at the top that's either bouncing light back or absorbing light. That's the orange color of your carrot. Is all comes right from that molecule. And what does it contain? Look at the size of the conjugated system here. Double, single, it goes all the way down the line. Okay, that's why it absorbs so nicely, and then you get that bright orange color. The molecule at the bottom, if you look here, that's the chlorophyll, and it has patterns of double, single, double, double, single, double. Okay, not all the way through the way carotenoid on top does, but if you see, it does have it, and that's why it absorbs the 2 different regions in the blue and the red. So if we can get absorption that's consistent with this, that would mean that the Europa Clipper has found more complex organic molecules there. That would be, again, the $5 billion treat. That there. Okay, now I was talking about, what about amino acids? Okay, always coming back to these here. If we could see something like this, this would be more practical. Okay, amino acids are small organic molecules. This would be terrific right here. It's this carbon to oxygen double bond in these molecules that give you the absorbance somewhere between 250 and 280. Okay, and this is just what amino acids just look like. This would be amazing to see something like this as well. Okay. Whoop. Okay, now let's talk again in 2030. Okay, I've just, I'd be so curious to see, but again, it's not only the data that's going to come back, but interpreting it, but things have to match up. So I'm curious to see what the analysis and the team of people that NASA is going to have to do all that analysis. But I know I covered a lot, but we'll see what happens, but what's up there. But I'll be happy with water. Okay, I know they're looking for water. I'll take that. Yeah, well, yeah. Everyone's after the water. But we'll see and if there's something in the water, not like New York City, but if there's something in the water, we'll find it for sure. But it's like I said though, as a chemist, and having taken courses on spectrometric methods, okay, you can't get the compound past the chemist. It's almost the forensic scientist. You can't fool anyone anymore. It's just, science is just too good. Okay, if it's out there, we'll find it. And yeah, so, but good luck to them. But I heard, just as a side note, some rumors on the internet that NASA the Europa Clipper may not be suitable for the mission because the circuitry may not be correct or whatever, or may not handle magnetic fields. I find that hard to believe. How many times we've been around Jupiter or Jupiter? You got to be kidding me. I'm pretty sure the engineers know what they're doing. If it's a $5 billion, there's no way it's a $5 billion disaster. No way at all. So, okay, I'm done. So, thank you for having me. I hope it wasn't too much chemistry. Sorry about that, but thank you. Yes, sir.
This hasn't been launched yet.
No, I believe it's, I think they said October 10th is the target date. Okay, and they said data will come back in 2030. So I think it actually has to go to Mars. It has to loop around Mars, then use Earth as a slingshot, and then it'll travel to Jupiter. And it's only gonna make 50 passes around Europa. So is that enough? The instruments are so sharp and cutting edge. It should be able to get all the data it needs in that time frame. 2030. So that's why I'm reserving for November 2030. Okay, so I'll be at your meeting. Yes, sir.
Do you know how close it has to get to Europa in order to scoop up the?
I don't know offhand. No, not offhand. But these particles, it'll find them for sure. So when you go on NASA's website, it almost makes it sound like the mass spectrometer. The way it opens, it's almost like they describe it like the movie Jaws. Like the innocent people just all of a sudden it's going to open its mouth and collect samples. Okay, it almost gives you that Jaws like movie thing from the 70s.
A regular spectroscopy of what we do from Earth.
Yeah.
You can see some, just by the light that comes back.
Yes.
See some, but I guess the mass spectrometer is much.
Yeah. Mass spectroscopy was, again, we don't use one thing. I mean, the first thing I always went with was infrared. Okay, and then there's something else here I didn't talk about. It's not on there. I don't know how you could even, for you guys going into college, you younger people, if it's out there, if you can get nuclear magnetic resonance on one of these things and do an analysis with that would be smoking hot. But it's tough to do. Tough to even prep those samples on Earth. But to do that in space, I don't know how I'd even begin there. But the mass spectroscopy, once you have hold of that, I could start looking at fragments that are most stable and pieces that aren't stable and fall off. Yeah, once I have like 4 or 5 pieces of spectroscopy, it's lights out. Okay, and I'm talking like one of the chemicals my professor gave me was BHT. Okay, and you think about this compound, when I finally figured it out, I was like, this is BHT. Where the hell have I seen this stuff before? It's in your cereal. It's the preservative in your cereal. I'm like, you mean to tell me this is what I eat? It's like, oh God, it's like, so you would eat it on your Wheaties. And here I am thinking like, I'm going to be on the box like this someday, NHL champion, but that's out. But 5'5", forget it. But anyway, and then you see yourself, would I take a spoonful of this stuff and eat it right here in the lab? You're out of your mind. Yet a little bit at a time in my Wheaties, I do. But just when you get to the structures, like holy cow, what you can decipher using this stuff, and it makes sense why 4 instruments of the 10 are based on spectrometric methods going up. Okay, so you can do a lot of analysis with these machines. Okay, got a question? Yes, sir.
I tell was not someone can pick up gases. You pick up basically what's above the surface.
Right.
Then the infrared's picking up like what's on the surface.
Right.
Is there anything can actually pick up what's under the surface?
I think that was excuse me 1 second, sorry, I didn't mean to do that to you. Okay, that was this one here. Under the surface was the magnetometer and the sound penetrating the sonar. Yeah, I think that was designed for under the surface. Those were your instruments.
Can you be just as true on the chemical?
No, not from these, not from sonar. And magnetometer, no, I don't know. Not that I've ever seen. Oh yeah, absolutely better than nothing. Again, though, everyone just wants to hear that you found water.
I think the sonar too,
I
was
just think
also
it's-
trying to figure out the depth.
Depth, yeah, depth of the ice, yeah.
Is there anything you could find where you just go instantly, okay, this means it's definitely like.
Oh, with some analysis, I don't think anything will be instant. Okay, we're gonna get back numbers. Actually, I'm hoping, not to be selfish, but I'm hoping NASA will post the data, not the results. This way, you know, that gives us people on Earth, the common folk on Earth to get a chance to look at it. So, but we'll see what it brings back. You know, we'll see. A question over here, yeah.
Correct me if I'm wrong, but haven't we already detected things like amino acids and other organic compounds in space?
Yes,
For instance, around comets and
I'm
other
has to
places.
have been done by now.
so, well, if we have discovered those, how are you going to distinguish something as a sign of life versus something that's all this random
Yeah,
stuff in space?
Yeah, that's a good question. And, you know, where did it come from? Right. Like where did our water come from? You know, it's so, but I'm sure NASA has a way of figuring that out. Okay. Yeah.
Part of this question has to do with how close do you have to get?
Yeah.
to
That
do
was
your
the other
sampling,
question that
because
came up.
I assume some things can be done at a distance, and I'm not talking about the distance between here and Europa,
Yeah.
but I'm talking about when you're in
Yeah, you
orbit
have-
of it, and whether you're at a point to do some of that spectroscopy is actually you have to be gathering some of the atmosphere that may be around that moon.
Yeah. I didn't see any mention of how far above it would be from the surface. And that was a question that was asked before. Yeah. Just how close it's actually going to get. I didn't see anything on that. But I imagine again, the closest, how many?
16 miles.
Okay, so that's pretty damn close. Yeah, but I would imagine the closer you get, the more reliable your data will be. Okay, but again, there's also that question of contaminants, you know, a pollutant, you know, the wrong chemical in the wrong place. So, but yeah, I'm imagining the closer they get. Okay, so it is up there. Okay, all right. So thank you for finding that. But yeah, I imagine it has to be close. The closer it gets, the more reliable your data will be. So.
You know, for 60 miles, could we get more by actually landing?
Oh, I don't know. That's a tough question. Yeah, probably. Yeah, sonar. Yeah, what you would find, I don't know. But landing.
That's where you see the light wearing the sunglasses.
yeah. That's funny, but I don't. This thing isn't coming back, so something's. I wonder if it's just going to spiral in and crash. I don't know what the outcome is going to be for this for the Clipper.
Crash that stuff right into Jupiter.
Yeah, yeah, but that's interesting to land it. Well, you ain't getting it back, that's for sure. So, but yeah, but to get that close would, yeah.
The farther away, the broader your view, but the closer, more sensitive, but the less you see.
Right. Yeah. So I imagine that's why your stereoscopic imaging will probably be done as it narrows in. So, all right, from the chemistry teacher. Okay.
Okay,
There we
uh,
go. Finally, one chemist to another. All right.
okay, well, I think with Europa, the UV and the infrared are easy because you can do it by reflectance
Right.
off the surface. The mass spec, obviously, the closer you get, the more you're going to collect. I think one of the hopes with Europa is that most of these ice-clad moons, like Europa at Jupiter and Enceladus at Saturn, they've seen geysers
Mm-hmm.
where the underneath water has broken through the ice.
Mm-hmm.
And so the hopes is if you can see a geyser and have the spacecraft fly through
through
the
it.
plume,
There you go.
now you've got something.
Okay.
The second thing is I know the European Space Agency is working on a plan that I guess would be a follow-up to Europa Clipper, whereas you're going to use sonar and map the thickness of the ice. So there's got to be thin spots somewhere,
Yes.
is to send the spacecraft to land on the thin spot and bore a hole
Oh,
through.
wow. All right. A tough mission.
And, you know, like that's a little bit more sophisticated, but then you get a lot more information.
Yeah. Yeah. The closer you get, the more information you'll get. But okay. Question, or no, you're just fixing the camera. Okay. Good. Okay. Anything else? I hope I didn't over chemistry you tonight. But again, if you have any questions or you want to, email me, that's fine. I eventually do read my email over the summer. Okay, if you get the message back, hey, I won't be back till August 25th. Don't be, don't be annoyed. I do get to my email eventually, usually once or twice a week. So, but again, thank you very much for having me back. And yeah, it's great presenting. So thank you. Thank you. Cheers. Oh.
All right, thank you so much. And Tommy shows up at an awful lot of our star parties too, so get to see him out there as well. That will complete our meeting for this evening for